Hi, welcome to this module, and in this module we will look at digital to analog converters. Now we have seen some parameters in the last module which were related to the conversion of the ADC to for ADC and for DAC as well, and what kind of parameters we had to use or we had to understand, such as Nyquist rate, such as quantization error, coding, right, sampling. So let us see what kind of DAC systems are there. Okay. So, if you see the slide, then there are two basic types. One is digital analog converters. When you talk about converters, there are two basic types. One is digital to analog converter and one is analog to digital converter. So, digital analog converter, if you see the slide please, then output of an analog voltage that is proportional to a reference voltage. This proportion is based on a digital word that is applied, right. A digital word is combination of binary ones and zeros that is applied at the input of DAC, that is your digital to analog converter. But when you talk about analog to digital converter, then a digital representation of analog voltage that is applied to ADC's input is given as output. This represents again proportional to reference voltage. That is how your analog to digital converter works. Very simple, right. The greater the number of bits in a digital word, the finer the resolution. Greater the number of bits in a digital word, the finer the resolution. The entire spectrum between 0 volts to reference voltage, which is V reference, is divided into sub regions depending on number of bits in the digital word. More number of bits, more the division in about spectrum, and hence finer the resolution. So, you understand that if you are asked a question how you can have a finer resolution in ADC, you can very clearly answer that by dividing the sub regions into more number of bits, and more number of bits relates to more number of division, and more number of revision relates to higher resolution. So, we need to understand difference between accuracy and resolution. The resolution of a converter is the number of bits in a digital word, okay, and where accuracy is number of those bits that meets the specifications. There is a difference between accuracy and resolution. So, you understand these two meanings. For instance, if you have a DAC which is 16 bit of resolution, but might only be monotonic, that is if it has 214 bits, this means that the assured accuracy of DAC will be no better than 14 bits, right. So, resolution can be 16 bit, but the accuracy will be 14 bit. While these terms are similar and sometimes used interchangeably, the distinction between two should be remembered. In this module, we will understand the digital to analog converters. Now, the basic block diagram of any DAC architecture is generally shown in this way, where digital is the input, there is a V reference voltage, there is a VDD, there is a VSS, and there is a ground, and output should be in analog format. So, the first DACs were board level designs built from discrete components including vacuum tubes as switching elements. Monolithic DACs began to appear early 1970s. And as in the figure, the digital word is given as the input, and analog reference voltage applied along with the supply voltage for internal circuitry, mostly consisting of operational amplifiers. So, these consist of operational amplifiers. They can be wired up using op amps, and discrete resistors are made up of monolithic chip as is available currently in the market. So, we can either make using the op amps and discrete components, or we can also make a monolithic IC. Okay. Now, we will look at two common DACs. Let us see two common DACs and understand which one is better than other. So, the first one we talk about is binary weighted network. Now, again if you see the circuit, it is similar to our adder. If you go back and understand how the adder works, or you can say summer. So, this one is a simplest form of DACs. An op amp circuit in the summing amplifier, right, summing amplifier configuration is used to implement it. Weighted resistors are used to distinguish each bit from the most significant bit. It is very simple: V1, V2, V3, Vn. We have a V reference voltage. Now, the reference voltage reference voltage is a set voltage, and according to that we can select one of these input until 2 raised to n minus r, and the weighted resistors are used to distinguish. These are the resistors which are R, 2R, 4R up to 2 raised to minus nr, right, each bit from the most significant to the least significant. Now, transistor based other types of switches are used to switch between V reference and ground, right. So, this switch now we are talking about, there can be transistor switch or other switches, and to provide the necessary binary 1 or 0. This circuit which is shown here, voltage is V1 through Vn are either V reference or 0 volt depending on the position of the switches, right. So, if it is connecting here, it is V reference, if it is not connecting, it is 0. Or if it is connecting in a different direction, because this one, let us say V3 is connected to ground, right. So, this will be 0. So, V1 is the MSB and Vn is the LSB. The expression for the analog output voltage is as shown in figure which aside, which is V out equals to minus I Rf, and minus Rf, what is I? I is nothing but V1 by R plus V2 by 2R plus V3 by 4R until Vn by 2 raised to n minus R. This is your output voltage. So, if Rf equals to R by 2, then we can write V out equals to minus I Rf equals to minus V1 by 2 up till this one. So, for a 4 bit converter, it will be B3, B2, B1, B0, and 1 by 2, 1 by 4, 1 by 8, 1 by 16, right, because 2 raised to n, 2 raised to n is 2 raised to 4, 2 raised to 4 is 16, right. So, you start with 2 raised to 0, then 2 raised to 1, then 2 raised to 2, then 2 raised to 3, like that. So, here is 2 raised to 1, because first bit is 2 raised to 1, 2, 2 raised to 2, 4, 2 raised to 3, 8 until 2 raised to 4, which is 16. So, now you do not have to really do until, right, because there are only 4 bit converter. So, the advantage here is that simple, it is very simple in construction, as you can see, it is very simple in analysis, and there is very fast conversion. Why? There are some limitations which requires large number of resistors with a high precision of for low value resistors. Low switching resistance is required in switching transistor and not scalable to high bit numbers, and resistor selection precision gets affected, right, because if you keep on increasing the value of resistor, as you can see here, until when you can increase the value of resistors, it is very difficult to have very high value of resistors. Same way, it is very difficult to have very low value of resistors as well. So, there are some of the limitations of the weighted binary network, but when you talk about R-2R ladder type DAC, which is again as shown in figure here, here what we do here, this is again shown for 4 bit DAC converter, each bit corresponds to a switch. Okay. So, you see here bit 0, bit 1, bit 2, bit 3. So, each bit is corresponding to a particular switch. Now, when a bit is high, the switch is connected to the inverting amplifier, right. So, if I connect this here, right, then it is connected to the inverting terminal of the operational amplifier, and when it is low, it is connected to ground like this, correct. Now, assuming ideal op amp, we get those configuration as shown in figure 4. So, for this one, if I use this particular square, right, what I have? I have 2R and 2R again here, right. So, what will be the R equivalent circuit? R equivalent will be 2R into 2R by 2R plus 2R, which is your R. So, if I put this value as R, then extending this with node V2, which is our V2 is right over here, right, then what we have? V3 equals to R by, because this is here, right, this one, and this guy is R. So, this is also R, right. So, the V3 will be R by R plus R into V2 equals to 1 by 2 V2. Same thing, if I go on extending, V2 equals to 1 by 2 V1, V1 equals to 1 by 2 V reference, V out equals to minus IR, substituting the values of the following relationship, what we get? V3 equals to 1 by 8 V reference, V2 equals to 1 by 4 V reference, V1 equals to 1 by 2 V reference, and expression of V out would be V out equals to minus R into bits, bit 1, bit 3, bit 2, bit 1, bit 0, and what we have? V reference by 2R, V reference by 4R, V reference by 8R, V reference by 16R. So, V out will be nothing but for a 4 bit R-2R converter minus V reference into B3 1 by 2, B2 1 by 4, B1 1 by 8 plus B0 1 by 16, where B3, B2, B0, B1 and B0 are 3, 2, 1 and 0 shown in the figure. Now, so if you want to have a generalized expression for R-2R ladder, that is your digital to analog converter, then what can I have? The general expression can be V out equals to minus V reference into summation of Bn minus I Bn minus I into 1 by 2 to the power I, where I equals to 1 to n, and the advantage of this particular R2R ladder is only requires two value of resistor, as you can see, either R or 2R, right, 2R, 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 R, R and R. So, we require either only two values of resistor, one is R and second value should be 2 times the original value of R, and hence can be made more precise and accurate, does not require high precision resistors. The disadvantage here is the conversion rate is lower as compared to binary weighted digital to analog converter. Now, we have to see DAC weighted binary network and R2R network. So, if you want to do the experiment to understand 4-bit R2R DAC, let us see how we can do it. Now, you can see here figure, right, which you can connect it, right, like I said, you connect this circuit and then you connect this circuit as shown in figure, use R equals to 1 kilo ohm, these are R values which is 1 kilo ohm, alright, and then you have 2 R values which is 2 kilo ohm, correct. So, cross verify supply connections, apply various 4-bit digital inputs. So, I will apply 0 0 0 1 or 0 0 1 0, right, depending on it will be connected, and measure the corresponding analog voltage and tabulate measure error of ENA. So, we can put different values like I said 0 0 0 0, analog port should be 0, error should be 0, 0 0 0 1, and then you have analog output which is error should be something. So, you have to do this experiment and measure the value of analog output at the output of the operation amplifier 741, and if there is any error you should measure the error as well, right. So, what we understood that we have two types of DAC, one is your R2R network and one is your binary weighted network, right. So, you guys when you read this particular module, understand this particular module, then see how you can design quickly R2R network and binary weighted network. Like I said, it is a very simple design and very easy to understand. So, try at home, try in your laboratory, it does not require a lot of components, and we will also show you how to design such kind of converters. In fact, we will use probably in one of the experiments that we have designed, if it fits within the 30 hours of this particular course. I will request now TA to help us with the circuit experiments, and I will request him to join us.
Now, we will see the simulation result of DAC. So, once we finish that, once we verify, then we will also look into the experimental one. So, in order to test the circuit and in order to compare with our theoretical values, we will go to multisim, we will create the same circuit using this circuit simulation software. So, now, so for our understanding, what I will do is that I will keep both the presentation as well as this one side by side. So, it is easy for us to visualize the circuit and easy to build us. So, if you observe carefully, we have to use a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 resistors, right. 9 before one resistor is in non-inverting terminal, and so I am also using the same 7.4 op amp, and I will be using the same even for the experiment too, and this is a negative feedback. So, what I will do is I will simply swap, okay, and I will choose resistors. So, if I want to choose a resistor, I will be going to resistance palette. So, I will choose all set of resistances here, 1, 2, 3, little bit I will move in this direction, 4 and 5, right. Then I also require one feedback resistor, so I am taking the feedback. Then I need resistors in this direction, 1, 2, 3 and 4, right. Now, what will we do? We also require these switches, isn't it? So, because it entirely depends, the output voltage entirely depends upon which switch is on. So, as we have considered in theoretical, first everything is grounded, then everything is like 0 0 0 0 0 1. So, we will, in order to make it 1 2, like to make the D0 bit as high, D1 bit as high, rather than stopping the simulation again connecting to 5 volts, what we can do is that we can do is that we can take a switch here, we can go with some SPDT switches, right. Let me reverse it. So, we will take SPDT switches in every cases. And what I will do is that one terminal I will connect it to the ground, and other terminal we will connect it to 5 volts. So, I will be creating DC voltage will be connected here. Okay. So, I will make it as 5. Right, other terminal should be ground. So, I slightly change the settings. I do not need this. Oh, okay, fine. So, we will make it as V1. Okay. Then so other terminal should be connected to the ground because of power supply, or what we can also do is we can connect from here. This is 5 volts and so this I will delete. From here I will connect to 5 volts, all one switches will be connected to the 5 volts. Whereas other will be connected to the ground. So, the default state is all D0, D1, D2, D3, in this case S1, S2, S3, S4 are in 0, but whenever I want to make it higher, meaning when I want to make it to 5 volts, only thing is if I toggle the switch, then it will connect it to the 5 volts. That means that particular bit is higher. So, that we can easily see. Now, I will make complete connections here, connections from here to the switch, all the resistance to switch. Now, these resistance should be all 2K. So, I will change it to 2K. Even this value should be 2K. This is also 2K, 2K. Now, so after doing these connections, and this also has to be changed, but this should be 2K. So, I will replace this with 2K. Then other connections I will be doing now. So, connect all your resistors. And this terminal should be connected here, whereas I will take one more ground and connect it here. This is because the positive terminal is connected to ground. Now, this particular point has to be connected here, this point has to connect here, this one to here, this one to here, whereas this particular point is ground, right. Now what we do, the feedback resistance is also 2 kilo. We will go here, we will change it to 2 kilo, and the output has to be connected to here. So this is my output and this is this one. Now what about power supply? Yes, we also have to provide a power supply. When you look into the details, so the plus Vs is this particular terminal, is it? So the three, where are the three terminals are there, this particular portion is Vs plus and this is Vs minus. So when I have to power it, I have to use this for Vs plus, right, again. So this particular bottom one is Vs plus. Now with that intention, I will take one more power source from here. I will connect this to this, as I am making it as 15. It is up to you whether to 15 or 12 volts, anything is fine, as long as the op amp can function for the rated voltage, you can use that particular value. And DC voltage, this should be 15, minus 15. So since the negative terminal is connected here, we do not have to make it as minus, but this value should be 15, then whereas other terminal should be grounded. Now to understand the value, what I will do is that I will connect voltage probe. Now, so as we know, as we have already seen how this particular circuit works, right. So as we have already seen, V naught is entirely depends upon the V reference value, right, V reference into whichever bit is higher, right, divided that part since minus V reference into summation of 1 to n b minus 1, whichever bit is higher, divided by 2 power I, whichever based upon the bit 1, right. Now what I will be doing is, since the reference value is 5 in this case, when we see 181 microvolts, so which means that this is this is almost 0. So when I make it as voltage and minimum as minus, okay, minimum as 0, maximum as 10 volt, or minimum as 5 volts and maximum is also minus 10, I will make it, right. We can see the output is 0. Now when D0 bit is higher, right, since it is an inverting type and the reference value is 5, right. So the maximum voltage will be 5. So what I will do is that this voltage will change it to minus 5 to 5. Right. So if I make all the bits as 1, right, almost close to 5. Okay. So what about my other values, right? When I see, so 4 cases we have considered. What are they? 0 0 0 0, right, 0 0 0 1, 0 0 1 1 and 0 1 0 0 0 1 1 1. We can consider any case, this is just for a testing purpose. So when we look into that relations once again, we can see that V out is nothing but minus V reference into B3 into B3 by 2 plus B2 by 1 by 4, B1 by 8 plus B0 by 16. Now when I make D1 as higher and all bits as grounded, meaning when I look into the voltage, only this particular terminal is higher, sorry, only this D0 is higher. So V reference is 5 divided by 16. So when I calculate 5 divided by 16, 5 by 16, the value is 0.3125. Now, when I look into this one, so 0.312 millivolts, right, makes sense. Now, I will make it as 0, 0, so this is the value for 0. This is the value for 0, 0, 0, 1. Now, why don't we do it as for 0, 0, 1, 0, 0, 1, 1. So, that means even D1 bit is also higher. When D1 bit is higher, so that means it is nothing but minus V reference into B by 16 plus B0 by 16 and B1 by 8, right, that is a relation, right. When I do that, the value will be 5 by 16 one value and another value is 5 divided by 8, right. So, when I do that 0.9375, right, the value is 937.31 milli. But what if I change my reference? Yes, if I change my reference, even the output voltage will change. Now, for example, like say if I take a 15 volts, if you observe for 0, 0, 0, right, for 0, 0, 0 it is completely 0, whereas for this 937 milli, right, whereas this particular value 1, 1, right, this is 1, 1, this is 2.81, 2.81, right. How? So, 15 by 16 plus, right, 15 by 16 plus 15 by 8. When we calculate 2.81. Now, we have done for 2. Why don't we take 0, 0, 1, 0, right. So, when we see 0, 0, 1, 0, that means 0, 0, 0, this is 1 and this is 0. So, what is the value for 0, 0, 1, 0? So, it is nothing but minus V reference into 15 minus V reference into B1 by 8, right. So, when I calculate it 15 divided by 8. So, 1.875, observe the output voltage 1.8748, which is also approximate, which is almost equal to the value 1.875, right. Now, we will take one more, which is 0, 1, 0, 0. So, 0, 1, 0, 0. So, this is 0, this is 1, but 0 and 0. So, what will be the value for this? When I see for this particular value minus V reference into B0 by 16, right, in this case S1. So, S1 is 0, 0 by 16, it is 0, then B2 by 8, B2 is nothing but B1 by 8, in this case S2, S2 is connected to 15, right, it means higher. So, B2 is 1, B1 is 1, 1 by 8, which means 15 by 8 is one value, right. And along with this we also have one more, which is S3, which is nothing but B2. B2 is also high, B2 by 4. So, this is 15 by 4. And what about the other one? Other one is connected to ground, which means B3 is 0, 0 by 2, which is 0. So, that means I should get a value as 5.625, but in this case if I see this is 0, 1, 1, 1. So, but whereas we have calculated for 0, 1, 1, 0, right, 0, 1, 1, 0, 5.624, 5.625, right. We will go with the other one 0, 1, 1, 1, all 3. When we see to this we have to add 15 by 16, right. So, I will be adding 15 by 16. So, which is 6.5625. Now, what if I make all 1? So, what I will do? I will make everything 1, this also to 1. Now, what should be the output voltage if everything is 1? It should be somewhere around 15, right. So, why do not we calculate? We will see. So, 1 is 15 divided by 16 is one value, plus 15 divided by 8 is another value, plus 15 divided by 4 is another value, plus 15 divided by 2 is the last one. When I see it, I should get it as 14.0625 is the value output voltage that I should get when all switches are on, D0, D1, D2, D3. That means in this case S1, S2, S3, S4. But now why it is not showing it as 14.0625? The reason is that op-amp. The op-amp has been powered by using 15 and minus 15 volts, and the reference value is also 15. So, the maximum voltage depends upon op-amp. The maximum voltage is always lesser than the supply voltage, right. That is the saturation voltage. Since it is a 741, the saturation voltage even lesser than that particular value. So, that is the reason when you see it has already gone to the saturation. What if I change to 5 volts here? Why do not we check? So, if I change to 5 volts, the reference is completely changed. So, since the reference is completely changed, now the value will be, so 5 divided by 16 is one value, and other value is 5 divided by 8, then other value is 5 divided by 4, 5 divided by 4 plus 5 divided by 2. These are the values. When I calculate it, 4.68, right, 4.687, right. So, the previous case, why it has only showing 13, the reason is because of the saturation. So, one important consideration is, whenever you are working with an op-amp, you have to see what is an expected voltage, whether the expected voltage is lower than your saturation voltages or not, right. Now, so since we are calculated our complete theoretical output voltages using a reference as 15, I am going back to the 15, right. So, that is why it is showing it as 13. So, we will make it as last one, we will say 1110, meaning D naught bit is 0, but except but D naught bit everything is 111. So, what should be the value? If it is a case, we will calculate. So, one is 0 divided by 16 because of B0 bit, and other one is 15 into 1 by 8, right, V reference into B1 by 8 plus V reference into B1 by 4, B2 by 4. So, divided by 4, B2 is high already. Then other one is V reference into B3 by 2. When I make everything 13.125. So, this is also approximately 12.996. I will also do one more. This is also 0. Now, we will calculate even this. So, in this case it will be 15 by 4 and 15 by 2. So, the value is 11.25. So, we can see it is also equal to 11.25 itself, right. So, by using the simulation, we can, rather than even going with an experiment, rather than completely wasting our time by struggling where exactly we have done a mistake, if you look into the simulation, it is easy for us to understand, to do all the modifications. Once the final design is done, we can do the same experiment on the board, and we can cross verify our simulation as well as theoretical with our experimental data too. I hope so. The simulation part of our D2 R-2R DAC is done. Now, we will do the same, we will connect the same thing using the TI board, we will connect the same thing using breadboard. So, we will take a 74 op amp, we will use 2 kilo ohms resistors as well as 1 kilo ohms resistors, as we have connected, as we have shown in the PowerPoint, as well as we have shown in the simulation. We will do in the same way, same procedure, and we will see for test cases we have considered in our theoretical, we will also consider the same test cases in our breadboard too, and we will see whether even with theoretical and experiment whether both are matching or not, right. So, we will go to experiment now.